Welcome back to online lecture 2 of unit number 5, heat load estimation in building structure. So this lecture we will discuss the first method of estimating the transmission load, that is decrement factor and time lag method. Previous lecture we have we have discussed, we have studied some basics related with the transmission load. Mainly we content the descriptive part of decrement factor and time lag method, and the numerical based on the same method. There are generally two approaches to empirical calculations of heat transfer to walls and roofs used. And these two approaches are decrement factor and time lag. And the second one is equivalent temperature differential method. Both the methods use analytical experiment results for their formulations. But the equivalent temperature differential method is more commonly used by the air conditioning engineers, as it is also applicable to sunlit walls and roofs. So various tables are also available in carrier handbook or other data handbook for calculating the heat transfer rate through this particular method. But the decrement factor and time lag method is regarded as one of the basic method, because on this method the ETD method is developed based on by using some simplified relation. But the basics of the heat transmission through building is mainly from this particular method, that is decrement factor and time lag method. Decrement factor and time lag method is mainly used for calculating the heat transfer through structured wall. Here we are not considering the glass wall, only the walls are considered. Maybe the side walls as well as roof or floors. If the thermal capacity of the wall is ignored, then the instantaneous rate of heat transfer at any given time is given by this expression. So this is the instantaneous heat transfer rate, Qi, that is equal to UA delta T. So UA delta T, in that case, delta T is always the difference between outside air temperature and inside air temperature. That in the previous lecture, there was one mistake while mentioning TO and TI. Actually, in that case, it was not outside surface temperature and inside surface temperature. Rather, it should be outside air temperature minus inside air temperature. So whenever in the expression of Q, U term is there, that is overall heat transfer coefficient. So overall heat transfer coefficient, if we are considering, it consider the end temperature. So if the heat is transferred from outside air to inside air, so first heat is transferred from outside air to outside wall, that is due to convection, and then the heat is transferred from outside wall to inside wall, that is due to conduction, and from inside wall to inside air, that is again due to convection. So convection, conduction, and convection, these are the three modes involved in the transferring of heat. And all these three modes are associated with this U. So U factor takes into account all these three modes with the help of the three coefficients. So conductive resistance, then two convective resistances. But in this is overall heat transfer coefficient also. But if we consider the solar radiation effect as well on the outside wall, then instead of TO, the T is used. So this is, suppose the wall, this is outside surface and this is inside surface. So heat is transferred from outside air to inside air, and this formula is instantaneous heat transfer. But while developing this expression, we are considering T, that is sole air temperature. So sole air temperature takes into account the effect of convection as well as radiation to the outside air. So instead of TO, so TO is replaced by T, that is sole air temperature, and instantaneous, but at any particular instant, what is the rate of heat transfer? Suppose now it is 11 AM. So what should be the heat transfer at 11 AM? This is the instantaneous heat transfer. So this equation is applicable only if the thermal capacity of the wall is ignored. Means what this equation indicates, whatever the temperature, solar temperature that we already studied how to calculate solar temperature, considering the effect of convection, then radiation, and the air temperature. So what is the sole air temperature outside at a particular instant? The same heat is transferred at the inside. So the instantaneous heat transfer. So this is possible only when if the thermal capacity of the wall is ignored. So this is the interpretation of this equation. The instantaneous heat transfer is given by U8 delta T. So delta T in this particular case is the outside air temperature minus inside air temperature. So instead of outside air temperature, we are considering solar air temperature, because solar air temperature also takes into account the radiation part as well. Because TO, it takes into account only convection part. So that's why if we consider TO here, it takes into account the convection heat transfer, conductive heat transfer, as well as convective heat transfer here. But if we consider TE, it takes into account the combined effect of convection and radiation. So that's why this is UA TE minus TI. And the instantaneous heat transfer, the T indicates the time at which the heat is transferred. So suppose if the time is 11 a.m., so this is the heat transfer rate at 11 a.m. to the inside the room or inside the conditioned space. But this is possible only when if the thermal capacity of the wall means if we are considering the wall resistance or the thermal capacity of the wall is negligible. On the average basis, the same equation we can use, that is UA TEM minus TI, because T is the temperature at one particular instant. Suppose in a particular day there are 24 hours. So if we take all hourly, if we take the readings hourly, so there are 24 readings. So for example, this is a mean heat transfer for 24 hours. So obviously this is the TEM is the average of this 24 hours, 24 readings. So on the average basis, this equation can be used. But most of the building material have a finite thermal capacity. So already we have seen this building material. So this building material have a finite thermal capacity, which is expressed, and thermal capacity is expressed by this formula. That is, thermal capacity is mass into specific heat. So which is given by, so instead of mass is the density into volume. So volume is area, surface area of the wall into thickness of the wall. So this has a finite thermal capacity, means where we can say M is the mass, rho and C is the density and specific heat of wall material. Then A is the cross-sectional area of the wall. So obviously it is cross-sectional area, and delta X is the thickness of the wall. So this is the thermal capacity. So when we consider this thermal capacity has twofold effect on heat transfer. So the first effect, there is a time lag between heat transfer at the outer surface QO and heat transfer at the inside surface QI. So obviously if we see the heat is transferred because there is some finite thermal capacity. So this thermal capacity of the or the finite value of this thermal capacity of the wall, and due to this thermal capacity of the wall, the heat is transferred at the outside. Suppose at 11 a.m. immediately that heat will not be transferred to the inside air at the same instant. That is because of the thermal capacity. So there is some time lag. Suppose at 11 a.m. heat is transferred to the outside air or outside surface. There is some time lag. If suppose that time lag is suppose for 2 hours, 3 hours, depending upon the thermal capacity of the wall, the heat is transferred to the inside air or inside surface. That is after some time lag. Suppose if time lag is 2 hours, so the 11 a.m. heat is transferred to the inside at around 1 p.m. So the 2 hours required to transfer that heat from outside to inside. So that is called as the time lag. So that time lag is because of the thermal capacity of the wall. So that is the first effect. There is some time lag to transfer the heat at the outer surface and to the inside surface QI. There is a decrement in heat transfer due to the absorption of heat by the wall and subsequent transfer of part of this heat back to the outside air when its temperature is lower. So obviously, whatever the heat is transferred to the wall, part of that heat is absorbed by the wall. That is, suppose in the day hours, that part of heat is absorbed, so the temperature of the wall increases. And during night hours, if the outside temperature is less than inside temperature, so the part of it is dissipated, so transfer back to the outside air when its temperature is low. So because of that, the 100% heat is not transferred to the inside. Suppose, for example, 100 watt is 100 watt of heat is transferred to the outside wall. So 100 watt is not 100% come inside. Some part is absorbed by the wall, and some part is reflected back to the outside air, especially when the outside temperature is lower. So out of 100, depending upon the decrement factor, out of 100 watt, only say 60 watt, 40 watt, 70 watt, depending upon the decrement factor, that comes inside. So these are the twofold effect because of the thermal capacity. So instantaneous heat transfer doesn't take into account these two effects. Means it doesn't take into account the delay in heat transfer as well as decrement in heat transfer. So these two effects, if we consider, then the actual heat transfer at any particular time t can be estimated by using this formula. So Qt, that is equal to UA, TEM minus TI, that is average heat transfer. And this is the second component, which is also called as the periodic component. It depends on the various, depending upon the temperature difference between T minus 5 and TM. So this is a variable component, and this is the mean heat transfer rate. So first of all, we'll see that what is T minus 5. So T minus 5 is the solar temperature at time T minus 5. That is 5 hours before the heat transfer rate is to be calculated. Suppose if we have to calculate the heat transfer rate at 4 p.m. and there is a time lag of the time lag, it is indicated by a factor 5, and there is a time lag of 4 hours. Then while calculating the rate of heat transfer, this particular temperature T minus 5 is considered as this temperature, that is solar temperature, is considered at 12 p.m. So 12 noon. So 12 noon temperature we consider for calculation of heat transfer at 4 p.m. because there is a time lag of 4 hours. So that is the interpretation. So that is called the T minus 5. That is the solar temperature at time T minus 5. T minus 5 is the time at which the heat transfer rate is to be calculated, and minus 5 is the time lag. So if it is time lag is 4 hours and we are calculating the time heat transfer rate at 4 p.m., then we have to consider the solar temperature at 12. So that is the interpretation. That is T minus 5. So if we compare the equation 3 and equation 2, suppose if we consider these two equations, it shows that the Q, that instantaneous heat transfer, it can be greater or less than the mean heat transfer rate. And that it depends on the second term. If the second term is positive, then it is greater than mean temperature. If second term is negative, then it is less than. Now, when second term is positive, when T minus 5 is greater than mean temperature, then it is positive. And the vice versa for the second case, it is negative. Means if this is less than TEM, mean temperature, then this is negative. In that case, it is less than the mean temperature. So this is the interpretation. Therefore, the second term in the equation 3 represent the periodic component, which is equal to the sum of all such components. Means every hour, this particular temperature is varying. This is a constant term because it depends on the mean temperature, indoor air temperature, heat transfer coefficient, and surfaces. So all these for a particular day, this particular term is constant. So periodic variation, and that is UA lambda. So this particular term, it takes into account the decrement in heat transfer, lambda, because lambda is the decrement factor. Its maximum value is 1, lowest value is 0. So if for a very thin wall, the lambda tends to unity, and for very thick wall, it tends to 0. So the decrement heat transfer is taken, its maximum value is equal to this, so is 1. So if the value decreases, this factor decreases. So this lambda value is also taken into account that is decrement in heat transfer. And the time lag is also taken into account, because here, while considering the time, we are considering the deferred time, not a live time, instantaneous time. So both effects are considered in this equation, especially in the second term. Both effects are considered. That is, this particular term, it takes into account the time lag, and this particular term, that is lambda, it takes into account, that is called a decrement factor, it takes into account the decrement in heat transfer. Now it is evident that if the wall is thick, the decrement factor will be small. So decrement factor decreases as the wall thickness increases. Thus, in the case of very thick wall, the second term on the right hand side. So the second term on the right hand side in equation 3 can be ignored, and the equation 2 holds. Means if the for a very thick wall, lambda tends to 0. So if this term 0, the second term can be ignored, and the equation 2 holds. It means in that case, means for a very thick wall, the instantaneous heat transfer is close to mean heat transfer rate, that is UA TEM minus TI, which implies that the heat transfer across the wall remains uniform. Means even this is instantaneous heat transfer, but almost the heat transfer rate is uniform at its mean value throughout the day. It is therefore advantageous to provide a thicker wall in the buildings that are not air conditioned. So generally, if we see the old building structure of stone walls, the thickness is very large, and because of that thickness, large thickness, the building remains cool in summer and remains warm in winter. So such buildings will not become excessively hot in summer or excessively cold in summer. So if I don't know whether you have experience or not. So if not, you can experience that in the stone structure building, generally with the help of ventilation, that is with the help of fan also, we can provide the comfort conditions. Brick structure generally require air conditioning, because brick structure having a small thickness, and stone is also have high thermal conductivity. So lambda factor of stone is also very low. And also there is a time lag, and because of that, such buildings, stone buildings, are not become excessively hot in summer or excessively cold in winter. So this is generally happen in the stone wall buildings, and not in brick wall buildings. Brick wall buildings, exactly, air conditioning is required nowadays. Same thing, opposite condition prevails when the wall is too thin. If the wall is too thin, then opposite condition means the lambda value tends to unity. So this value is considerable, and the phi value also tends to 0. So in the limiting case, when the wall thickness approaches to 0, the decrement factor, suppose in this case, one wall thickness approaches to 0, the decrement factor tends to unity, and the time lag factor, it tends to 0. So for a very thin wall, suppose for almost 0 wall, it is close to 0. So if this is 0, so this is TE T minus TEM. So TM get cancelled. So if we resolve this particular equation, so for a limiting case, lambda tends to 0, lambda tends to unity, and phi tends to 0. So the modified equation becomes UA TET minus TI. So TM term get cancelled. This is unity. So UA is common. So it becomes TET minus TI. So this is equation 1 is applicable in that case. So for a very thin wall, equation 1 is applicable. For very thick wall, the equation equation 2 holds. That is mean temperature. That is, in heat transfer through a wall is equal to the instantaneous values. So these are two values we can consider for the extreme cases. For thick wall, generally heat transfer rate is uniform, and for a thin wall, the instantaneous heat transfer variation is large. So it is recommended to have a thick wall where the outside temperature variation is large, and thin wall, we can go for thin wall if the outside temperature is more or less uniform. Accordingly, for thick wall, the heat gain doesn't vary much. So this is the variation of thick wall. So we can thick wall, heavy wall with high thermal conductivity. So the heavy structure, we can say, even the thermal conductivity is high. The heat transfer rate variation is more or less uniform. Whereas for thin wall, it varies considerably for 24 hours. So depending upon the outside temperature, if the outside fluctuation is more, the same fluctuation that we have studied is seen in the first lecture slide, that variation in 24 hours. So this generally follows the curve of outside air temperature or outside solar air temperature. The effect of type of construction on heat again is also shown. So the light construction and heavy construction. Light construction means light wall with low thermal conductivity. Heavy construction means heavy wall with high thermal conductivity, as shown. It is said that light wall with low thermal capacity having a time lag of about 3 hours as the maximum heat gain at 3 p.m. and a great variation in heat transfer for 24 hours. So suppose for a time lag of 3 hours, so this particular heat gain, it arises, so whatever the 12 noon heat, it arises around suppose 1 p.m. if the maximum heat transfer is there. So the maximum heat arises at suppose 4 p.m. it arises because there is a time lag of 3 hours. And the great variation generally arises in 24 because during day hours the temperature, outside temperature is high. So obviously the heat gain is also high. During night hours the heat gain is also low because outside it. But there is some deferred. So even in this case, suppose the maximum heat gain arises at 4 p.m. and if there is a time lag of 3 hours, then this maximum heat is available at the outside around 1 p.m. This is interpretation of this. Heavier wall with high thermal conductivity has reduced and more uniform heat gain. You can realize here, and the peak hours much later, says at 12. So almost the peak hours, because there is a delay almost for 7-8 hours if delay is there. So peak hours, peak heat gain generally arises later, generally at the midnight. You can see here. So here the peak hours, peak heat or peak heat on the or peak load on the air conditioner due to this transmission that is arises around 4 p.m. And for heavy structure it arises at almost midnight, but that is at a lower heat rate. So heat rate is drastically reduced as well, but also the time lag. So from this we can say there is a time lag as well as reduction heat transfer for heavy structure, corresponding to almost a lag of 12 hours suppose. So here in this case we can consider the lag of 12 hours. A still heavier construction may result in very small and uniform heat transfer rate. So further we can reduce this heat transfer rate by having further heavier structure construction. Thus, in a locality where the daily range of variation of outside air is small, it is immaterial what thickness of wall is provided. So the outside variation is not very large, range is not very high. So during day and maximum and minimum temperature, then it is immaterial, of thickness is immaterial. In that case, only the pattern of heat transfer rate is almost same. But in a locality where the daily range of temperature is large, it is desirable to have a thick walls so as to cut the cooling load in summer and the heating load in winter. So the thick wall is generally recommended where there is a temperature variation, outside temperature variation. Moreover, such walls will not allow the inside temperature to rise very much during the day and drop at night. Thus maintain a reasonably uniform and moderate inside temperature even without air conditioning. So that, as we have discussed, without air conditioning also, it maintains a uniform temperature. Also in buildings that are not conditioned, night ventilation helps to maintain them cooler during the day. So as discussed, there are two effects: density. As the density increases, almost for a particular thickness, dense that provides more. This is a thickness, suppose up to 1200. So for a particular thickness, the time lag increases with the density. So and as thickness increases, time lag increases, and as it also increases with increasing the density as well. Suppose the effect of thickness here with the decrement factor. So as the thickness increases, decrement factor decreases drastically. And it tends to 0 for a very thick wall, and it tends to unity for very thin wall. I will take one numerical. So these numericals can be asked for almost 8 to 12 marks. So almost 70-80% portion is occupied by this numerical in the question. So you can rely on this numerical. There are very less varieties. More or less, we have to use the decrement factor and time lag here. So this is 25 centimeter thick wall is considered, is exposed to the periodic temperature and incident radiation variation on an hourly basis between 7 a.m. and 6 p.m. is given in the table. So in the table, the values of outside air intensities hourly basis is given. So we have to determine the average and peak load between 1 to 6 p.m. So what is the average and peak load between 1 p.m. to 6 p.m. on the average on the air conditioner, maintaining the room at 25 degrees Celsius per unit area of the wall. So area of the wall is given, that is unity. Also determine heat gain at 5 p.m. and the time of peak load. Use the time lag and decrement method. So some of the terms is given. So absorptivity of surface is given, which is generally required to calculate solar temperature. Thermal conductivity of the brick material is given. Outside heat transfer coefficient. Now here we are using HO and HI term. So you can use FO or FI as well. So this is as per the convention. General notations we are using HO and HI. So outside air temperature is 20. Outside wall coefficient is 23. Inside wall coefficient is 7. So obviously outside air is comparatively windy air and still air, that is 7. Average sole air temperature in this case is given. So maybe this is the average of 24 hours, 44.14 degrees Celsius. If it is not given, we can take an average of whatever the value is given in the table. The time lag is given 5 years, and the decrement factor is also given. So this is information is given. So this table is given, that is from 7 a.m. to 6 p.m. So for each time, the outside air temperature is given. So 7 a.m. it is 29 degrees Celsius. As the sun rises, the temperature increases. The temperature is maximum around 2 p.m. Sorry, not 2 p.m. It is around 3 p.m. and then decreases slowly as the time progresses during sunset. And similarly, the incident solar radiation, I, it increases with sunrises. So it goes to peak at 12 noon, then decreases slowly decreases. These are the values. Now, first of all, we have to calculate based on this information. First of all, we have to calculate the solar air temperature, because UA delta T required the instantaneous solar air temperature, that is obtained by formula TO plus absorptivity, I value, and HO. So A and HO values are constant for each reading. So only the variation in TO and So if we consider the A value absorptivity is given in the numerical, I values are also known to us. HO value is also given in the statement, that is outside heat transfer coefficient. So based on that, we can calculate the values of T. So if the average temperature is, average solar temperature is not given, TEM, we can calculate the average by averaging all these values. But in this problem, the average value is given. Now the mean heat transfer, which is asked, that is mean heat transfer is given by UA TEM minus TI. So TEM is already given, that is 44.74. TI is also given, inside temperature is 25 degrees Celsius. A is given, that is 1 meter per 1 meter square. U value is not given, but we can calculate the U value based on inside heat transfer coefficient and outside heat transfer coefficient, as well as the thickness of the wall is also given. Thermal conductivity of the wall is given. So that U value is coming around 2.838. So by considering this U value, EM value, we can calculate the mean heat transfer rate. So mean heat transfer rate is 54.21. Now, when the heat transfer rate is maximum, that is what is the peak heat transfer rate, and the time is given, that is 5 hours. So maximum heat transfer rate, that is when the heat transfer rate is maximum. For that, we can use the formula of instantaneous heat transfer, that is actual heat transfer rate. So mean heat transfer plus periodic component. Now here we have to choose, because mean heat transfer rate is already calculated here. Now U value known to us, A value is 1 meter square, lambda value is given 0.45. Now there is some confusion. Crux of solving problem, how to decide this T minus 5. Now this depends upon the time lag. Now time lag is given 5 hours. Now first of all, we recognize when the T is maximum. So when the T is maximum, the rate of heat transfer is maximum. Now if you observe these values, so the maximum value arises at 1 p.m. Sorry, at 12 noon. 12 noon, the solar temperature is maximum. Even the outside temperature is maximum at 2 p.m., but the solar temperature is maximum at 12 noon, because it is a combination of solar heat and outside air temperature. So obviously, the maximum heat arises when the solar temperature is 73.28. Now means this is T max. So the formula becomes Q max, that is equal to this UA lambda T max. So instead of T minus 5, we can use the expression T max. So if we put the value of T max, that is 73.28, TM value known to us, it is given in the statement itself. This value we already obtained, the first term. Lambda value is also given 0.45. So T max, so maximum rate of heat transfer we can calculate 91.77. So when this heat arises, because we have considered the temperature at 12 noon, but the time, so because there is a time lag of 5 hours, so this heat is transferred to the inside space 5 hours after this. That is, so after 12 noon, because 12 noon, this is the solar temperature outside, but the rate of heat transfer arises at inside space 5 hours after that. So 5 hours after that means what? So that is 1, 2, 3, 4, 5. So at 5 p.m. the peak load arises. The peak load occurs at 5 p.m. because that is 5 hours later. That means while calculating the heat transfer rate at 5 p.m., we have to consider the temperature at 12 noon. The second numerical actually it coincides. So suppose if we have to calculate the heat transfer rate at 4 p.m., then which temperature is to be considered? So not 52.89, because 52.89 is the temperature of solar at 4 p.m. that is outside. But while considering the temperature, we have to consider TET, that is at time 4 p.m. minus 5 hours. So while calculating the rate of heat transfer at 4 p.m., we have to consider the temperature 5 hours before. So we have to consider the temperature at 11 a.m. So here T minus 5 value is 70.18, not 52.89, because 52.89 is the temperature, solar temperature at 4 p.m. But while calculation, because of the time lag, we have to go back 5 hours, that is at 11 a.m. and we have to consider the temperature at 11 a.m. So this way we can calculate the temperature heat transfer rate at any particular time. So there are generally three questions asked. First, what is the mean rate of heat transfer? What is the maximum rate of heat transfer? And what is the heat transfer rate at one particular time? So in this numerical, the heat transfer rate is given maximum heat transfer rate and the heat transfer rate at a particular time, that is 5 p.m. it is asked. So heat transfer rate at 5 p.m. while calculating, we don't have to consider the temperature at 5 p.m. We have to consider the temperature 5 hours before. So that is at 12 noon. That is 5 hours before. So in this case, it coincides, but most of the times you can consider the time according to the timeline. So this is the way we can solve the problem. So these are the standard problems. In some cases, maybe this is a brick conductivity is given, maybe some plaster is used. In that case, you have to add this conductive resistances. That's it while calculating U. So these are the variations only, nothing else. So these are the three parameters generally asked. What is the mean rate of heat transfer? What is the maximum rate of heat transfer? And what is the heat transfer rate at any particular time? So this way we have calculated that peak load arises at 5 p.m. So this is a decrement factor and time lag. So for this is used for calculating instantaneous heat transfer rate as well as mean heat transfer rate. And also with the help of this technique, we can estimate or investigate when the cooling load on the air conditioner is maximum. So depending upon the variation in time. So the weather data, what we have studied in 4th unit, weather data is especially required for these two methods, that is transmission load. So at the end of this particular topic, you should be able to discuss what is this method. You should be able to explain what is decrement factor and time lag method, and also discuss the variation of heat gain in 24 hours. So why for thick wall and thin wall, generally for light construction, medium construction, why there is a heat variation. Then you should be able to determine instantaneous mean and maximum heat gain in the through the wall or in the room. So this is for particular wall. So if there are number of walls exposed to the sun radiations, depending upon we can calculate. So so with this, we have completed the first method. So next lecture, we'll discuss the second method, that is ETD, that is equivalent temperature differential method, which is mostly used by engineers. So, but again, that method rely on the first method, that is decrement factor and time lag, because the fundamental method or the principal method, we can say, that is the time lag and decrement method. So understanding of the total heat rate of heat transfer, you come to know only with the help of this method. So thank you very much. Next lecture, we'll discuss the second method. Thank you.